Okay, so in this segment, I'm going to show you the array sum in OpenMP. And it's remarkably simple, but I'll have to point out a few things. And I used it, for whatever reason, I used integers. I just did it at a different time, but it doesn't make any difference. So let me open up my Linux terminal. Okay. So this is going to be the same thing where I have an array, which this is going to be represented by this pointer um, to an int a, and it's going to be of size n, and I'm going to malloc it here, right, of size n. So I'm going to have this big integer array, and I'm just going to sum them all up. So I shove some random values in it, whatever. I'm just trying a bunch of different things. When you do testing, you obviously don't want randomization, by the way, but I had some goal at the time. I forget what it was. And I want to compute the global sum of A. We know what the serial code looks like. Well, here comes the OpenMP code. First, let me just point out that the serial code is right there. Okay, it hasn't gone anywhere. And I'm just going to start working around it now. So I say, okay, pound pragma OMP parallel. This is going to enter a parallel region. Now I'm going to be verbose because I want to be explicit as we're learning. So I'm going to say I don't want to rely on any defaults. That's what I was telling you in the last segment of visibility. By visibility, I mean private or shared or first private. So I want to say I is going to be private. Okay, well, where is I defined? Let's see. I guess I defined I up here. Okay, so I would not have been private unless I said it, actually. If it were declared in here, it would be private by default. So if I is private, you might say, well, why not first private? Well, because I'm setting its value for each thread. Okay, as long as you're setting its value, then you don't have to use first private, which requires its value to be initialized in a specific, which states that you want its value to be initialized in a specific way. Okay, so A, the array, N, the size of the array, and the global sum are all going to be shared variables among threads. You don't want each thread to have a private copy. There's no need. Okay, you're just reading N, you're just reading A, and global sum is the one thing you're producing. Sum is going to be first private in the sense that I want all of the threads to have the initial value of sum, which is 0. Okay, so that's because I'm doing a plus equals. Okay, so I want to make sure they're all initialized to 0. Then I've created my parallel section. Remember, I can collapse these two if I want, but I'm just being explicit. And then I'm going to say, okay, pound pragma OMP4, just so you see it broken out. Oh, I can't, I'm sorry, because I have more down here, I do have to separate these two. This only works when I'm just applying it to this loop. Otherwise, I'd have to open up. I'm not sure how I do it. So you really only collapse them when you just have one loop and nothing else that you're doing. Okay, so that said, this loop then gets parallelized and it creates the local variable sum for each thread. And then I'm still in the parallel region and I do an atomic sum of sum into global sum. And that has to be atomic because global sum is a shared memory location. Okay, and it has to be shared because that's what I want to do. I want to collect everything in one place. And then I end the parallel region, so it's perfectly fine OpenMP code. The idea is it's incredibly simple. I'm just annotating and depending on the compiler. So, I should use the same initialization that I used, although the other one was float, but it doesn't matter. I'm just going to sort of show you how to run it. I'm not so worried about it. I'll let you play with it and make sure the result is right. So mine is GCC F OpenMP array sum. Okay. I can't remember how I specified the number of threads. I should say that also. So let me open this back up. I don't see that I specified it anywhere. It's kind of odd of me. So there are a number of ways to specify how many threads you'd like to use. Okay, so why don't we do this? Why don't we say NT equals A to I argv2. That will be the number of threads. I'm just assuming that we passed the right number of arguments. I don't really have time for error checking. Okay, so I'm going to pass the number of threads. You say, well, where do you put that? Well, there are really 3 different places you can put it. But the easiest is there's a clause right here, which is num threads nt, and that says execute this with nt threads. And nt obviously can be a variable. So let's see how that goes. I did something slipping my mind what I did wrong. Let me look at it for 1 second. Okay, I don't know what's wrong with me. I have Fortran brain today. It is num threads. It's just lowercase. It's case sensitive. Not quite sure why I was thinking that way. All right, so now that we have that, we specify the number of threads, we compile it, and now I can say the size, and I can say the number of threads. So I can use one thread. Now this, this is idiotic, this randomization. Oh, I guess I didn't change the seed. All right, that's good. So I get the same answer regardless of the number of threads, is the idea. And you can test that you're using multiple threads, but I'll let you do that. It seems to be working. Another way you could do it is you could say OMP set num threads nt, and you can get rid of it here. This would override it. Yeah. I'm just going by memory, and unfortunately I'm not doing well. So let me try to remember the name of that function. Give me 1 second to look it up. Okay, here was the issue. I hadn't included the header file. And so it didn't matter as long as I wasn't calling any functions. But once you're calling functions, it doesn't see the prototype and it gives an implicit function declaration warning. Okay, so always include omp.h header file. Sorry, I neglected to say that. And once you do, then this line, I did have it correct. I didn't have the name memorized wrong after all. So if I run it like that, obviously there aren't 300 cores, so and once you start using more threads than cores, it's going to add multiple threads to a core to no performance benefit whatsoever. But anyhow, that's the idea. So let's look at, that's version, what I'm calling version 1 of the notes. Let's look quickly at version 2. I use a slightly different strategy. I use the reduction. Okay, so everything else is the same. Again, I'm being pedantic about the visibility of the variables, but then I say this is going to be a reduction, this parallel region on sum, and it's going to be a parallel for loop, and otherwise it's just fine. So I don't have to do the atomic collection of the GSUM. I can just add the reduction. And again, this is usually all just put on one line. It's a little funny to see it broken up this way. There's really actually no reason. Maybe after I end the segment, I'll go and I'll collapse it, but it's fine. You can write it on 2 lines also. Let's just make sure it works. So I'll just use the same compilation line. And unfortunately with this one, not sure what I did with it. I have to look at how I'm initializing the threads and so forth. Well, I should. Never specify the number of threads again here. So I'd say num threads nt. And I shouldn't waste your time with this, but just take a second. Okay. Why I had that one funny answer. So let's say I do 1,000 points with 1 thread, 2 threads. Okay, well, that's the idea. Okay, so obviously OpenMP, if you can convince yourself you can get comparable performance, it's really, really nice because it's an approach that relieves the programmer of generating the kind of redundant plumbing and lets you think more about the parallelism that you want to extract from your application. And so oftentimes I find when I'm doing OpenMP coding, I spend a lot of time thinking about exactly what I want to do and very little time implementing it. And it doesn't get rid of race conditions, no. It gives you a little bit of an easier job in tracking them down maybe. But it does free you from having to write so much tedious code. I think it's been very, very successful for what it does, which is limited, I admit. Okay, so I think that we'll leave it there then. And your goal now will be to try to apply each of those programming models to a fun code. which is a code that I chose because I want something that needs to be sped up. So the first thing you want to think about is how long does it take to execute this code for how many particles. You see that it's an n squared algorithm, so it grows fairly quickly. And then you want to develop a parallelization strategy, and most importantly, a testing strategy. You want to make sure you get the same answer, and you want to think, what does it mean to get the same answer? What is a reasonable thing to expect? All right, so I'll leave you up to that, and I'll happily add any other segments on details that you'd like me to talk a little bit more about.